So that's the big picture here, and now I'm going to diverge a little. I'm going to digress a little now and tell you a bit about exoplanets in the media. Because people are so desperate to find a planet like this that weird things have been happening. And I thought you probably have heard about this, and I'll try to explain about it. People go crazy over things like this. And also will help me explain to you how exoplanets is viewed in the world around us. There's a system called GJ581. And by the way, this previous picture, an artist made this. A bunch of artists made a bunch of pictures about GJ581c. That's a planet that was discovered, I think it was around 2007. It made news headlines around the world. It wasn't transiting, but people believed it was a big Earth orbiting a small star in the Habitable zone. This was pretty exciting. It turned out that the authors fudged things a little. The discoverers put in their paper that the albedo, it would have to be a very, very reflective planet in order not to be so hot that it was too hot for water. It actually pushed it a little bit. When other people took a closer look, it turns out it's too hot. Can't be one. Can't be one. So the artists made that picture for GJ581c. Now later on, more recently, GJ581g made the news, which is a smaller planet. You see there with the question mark in purple. And that one was claimed to be in the habitable zone. It kind of made it a massive atmosphere. It had to have a massive greenhouse effect. And that made news headlines all around the world. Now, reporters, people with journalists, they often don't remember from a few years ago because, news happens. They have to write a story and they're done. And then the next day it's different news. So that kind of tends to go away. But the people who were writing about this for the first time and hadn't written about the planet 2 years earlier, they would research. And I got calls from all these people. They'd say, well, what's going on? We thought this happened 2 years ago. And I'd say, no, actually, that one was wrong. And so here's another one that actually is extremely controversial in the community. And I'm going to explain that in a minute. But I just want to finish talking about the news. So what's interesting about this planet, GJ581g, it made news all around the world. And it astounded even me in terms of the public's reaction, just even to the idea of a planet that might be Earth mass and might be habitable. And what it did was, people not only wrote about this, but in the weeks following, I heard from way more journalists than I usually hear from, maybe 20 of them. And none of them wanted to talk specifically about this planet, because beyond a few days, it's old news. They wanted to do, many of them, it was in the woodwork that they wanted to do a radio show or TV or documentary or some longer article in a magazine about exoplanets. And this particular one, GJ581g, just pushed them over the edge. The fact that there were so many people waiting in the wings to do something about exoplanets, I was shocked, actually. Perhaps I shouldn't have been. The level of public interest in this, it was just phenomenal. Especially because now it turns out it's probably not a planet. It didn't matter, right? It just illuminated the fact that all those people out there, they're interested in exoplanets, they're just kind of waiting for the day when we can deliver some great news. So I'm going to try to explain, without a graph, what happened technically. And it actually illuminates a lot of problems that we have in science in general. And when do you make an announcement? Or when do you decide to wait? Someone else might scoop you. So what happened here was, my colleagues Paul Butler and Steve Vogt, and they've been looking at GJ581 for many years, a decade or more. And the way you find planets is with the radial velocity technique, but they're looking for a signal in the data, and they find the biggest planet in the data, and then they remove that one. And they look at the data again for another pattern, find the next biggest planet, and remove that. And keep removing and removing and removing until you're down to the last one, and there you go. Now, they did a couple of things that we think. Okay, they did two things that were not scientifically accurate. And one of them was they assumed all the planets were on circular orbits. And so they removed the signal of each planet, assuming it was on a circular orbit. Okay? And for people who aren't in astronomy or aren't scientists, I want you to think about an ellipse, like an oval. And if you were to subtract a circle from that, cut out a circle from an oval, you're actually left with something left over. And so in fact, if you're assuming the orbit is circular and remove that from the data, you could be left with another signal still in the data. And that actually could end up, it could end up showing up as another planet. Okay, so that is a problem. And they should really have done the analysis using eccentricity as a free parameter, and they didn't do that. The other thing was, if you look carefully, it was a less than a 3 sigma. I'm going to be technical first, then I'll explain it. Less than a 3 sigma detection. Okay, so what that means in terms of likelihood to be correct is the following. But we're 3 sigma. It was actually less than 3 sigma, but we're 3 sigma. That's basically a 99.7% chance that it is a real signal, and a 3 part per thousand chance that it's not a real signal. And this is kind of the dividing line in science of what we, at least in astronomy, consider acceptable for publication. And if you're really great, oftentimes that will be proved to be correct later. But I would explain this to the public by saying, would you get on an airplane if I told you in a 3 sigma, or that's a 99.7% chance that your plane will make it to your destination? People, if I say 99.7, people will say, okay, yeah. But if I say that actually means there's a 3 parts per 1,000 chance that it won't make it. And everybody says, no, it won't do that. That's a lot. I don't know how many flights there are a day here in the US. Probably 500. I don't know, maybe there's 1,000. So that means that we have one plane crash a day. That's a lot. So that's the certainty here. So I don't know, would you publish a huge announcement at that level? The part I didn't tell you was that I told you they take the data for a decade, and they need a lot more data to know one way or the other whether it was sure or not. So this is a judgment call here. Are you going to publish this at that level where there is some uncertainty? It's acceptable level. It's not like very robust or anything. It's kind of barely acceptable. Or are you going to wait longer? So what else might find out? This is a really big problem, and it's unresolved actually. This will happen sometime later on. So I'll just show you an example of what happens in the media. Most of the media don't bother following up. To them, it's a done deal. It was found, and we're done. Here's another one. So Phil Gregory of BBC loves statistics and be using analysis, and he looked at it carefully. He looked at the data and said, for the time being, the world does not have data that's good enough to claim the planet. But another independent group said, with the data we have, the most likely explanation is that this planet is still there. And I chimed in, and I just said, people want you to say something controversial one way or the other. I tried to be neutral. I said, I'm not going to admit that it's a dead planet yet. We'll have to take some time. But even I don't know what take some time means. I mean, if you're a scientist, are you going to spend your precious telescope time now, like looking at this planet for another 5 years just to prove it one way or other? Or are you going to spend your time looking at something that you think is a sure thing that will result in something? So I just wanted to give you an insight on some of the things that go on in exoplanets and how people, judgment is a really important issue. And let's go back to Carl Sagan to close this part of the discussion about extraordinary claims require extraordinary evidence. This is really true in exoplanets, but then we're back to the problem that the planet is so small and so weak compared to the star that is a problem. So when will we find another Earth Part 2? A big Earth transiting a small star? I believe within 1 to 3 years. I don't have any secrets here. I don't work on the observational side of this problem, so I don't know if anyone has one. But I think one of these will be found very soon, actually. And so if you hear about it, you think back to this talk and the discussion. And try to look at the data and see if it's 3 sigma, but the probability is that it's real. So to summarize this part of the talk, two-pronged strategy, transient planets with a focus on M-dwarfs. That's what we call the fast track, ground-based and planned space assets. Then we have this other prong 2, direct imaging of sun-like stars, which will require technology investments in new space-based facilities. So this is the big picture in the whole bulk of my talk about the progress and search for habitable worlds. This is the plan, and this is being carried out at all levels by lots of different people in exoplanets. Now to finish off, I just had a few slides because I wanted to tell you the questions I always get asked related to this topic. The next one I had is, can we go there? So I think most of you know the answer, but I'm still going to go through it because people love this question. I love this question. And it gets asked over and over again. Even if I talk about it, people will still ask me about it. So to do this, I'd like to start talking about distances, assuming that this is our sun. And I know most of you are an educated audience, but I just want to go through it as a sort of light way of the talk. If this is our sun, and this is a real picture of our sun, how big do you think Earth is in respect to this picture? There's actually a clue on the picture. Yeah, the little black dot. That's actually a sunspot. It's a real picture of Earth, and I had to dig around to find one that actually had the right size sunspot. I think it might be a little bit big, but there it is. Then the question is, well, how far away would Earth be? If that's the size of Earth and that's the size of our sun, where would the Earth be in a scale model? And since you are a sophisticated audience, someone should be able to guess. And put your hand up if you think it's where you are sitting in this room. And I'll help you out with some math if no one knows the answer. You're welcome to just guess. You think it was in LA? Okay, no, it's not in LA. It's actually not too far. And actually, if you can think, I bet some of you even know how Earth's radius, or the sun's radius, or Earth's radius with the definition of an AU. Well, actually, it's about 100 solar diameters away. I always get this mixed up by factor of 2, so you can check the math while we're figuring out where that is. 100, so 100 suns, where would that be? It's not in this room. I want someone just to guess what it is, because I don't know the campus well enough to say, oh, that is Avalon. South Lawn. South Lawn is too far away, but it's somewhere outside. Okay, so that's somewhere far away, 100 sunlight, that's zero. It's not too far. And the next question will be, well, where is the next star? Where would our next star system be? We had a good guess over LA. It's always good to do something with LA, right? It's pretty far away, but it's still the United States. So yeah, the next star would probably be about LA. That's really far. Think about it. If our sun is this size, next star is that is so super far away. Very, very, very far. And so we like to ask, what would it take to get there? Well, Voyager 1 spacecraft is traveling through space at about 20 kilometers a second, not an hour, a second. Very, very fast. And at that rate, if it were pointed in the right direction, it would take 70,000 years to reach the nearest star. A very long time. That doesn't even include slowing down. So actually, Alpha Centauri is about 4 light years away. And some people somewhere believe someday we will be able to travel at the 10th the speed of light. And that's more tractable. If we find an Earth around Alpha Centauri, it would take 40 light years to get there. We'd have to find a way to slow down and orbit and slow down and take some pictures. And then it would take 4 years for that signal to be transmitted back. And I actually really think that's tractable. And I know real people who are really thinking about this problem. And they're waiting for the day that a planet is found around Alpha Centauri to launch something out to go there. And this is sort of the far out part of the talk, but really, I mean, think about that. 40 years. There are people in this room. For 40 years, you'll still be here. You're not only will still be here, but you'll still be relatively young. The sort of scheme of life expectancy. Now, whenever I give a talk to undergrads, and this room doesn't have too many undergrads, I always say, this is pretty exciting. What if there are 3 independent groups monitoring Alpha Centauri as continuously as they can from their observing site. One of them is my colleague Deborah Fisher at Yale. She has a dedicated telescope in Chile. And they believe that if there's a bigger Earth orbiting Alpha Centauri b, a little bit closer to the star than Earth is, a little bit bigger than Earth, and if the star is quiet enough that with 3 years of signal, they can find it. And they might, if it's there, they'll find it. And at that time, that's pretty exciting. So what if we did have a way to travel at the speed of light? I would ask them as undergrads, would anyone be willing to volunteer to go there? Yeah, you've got one. And at least there's at least one person in the audience who will go. And you'd be giving up the prime of your life, right, from age 20 to 60. And they'd still go to be the first one to visit another planet. And I just love that because it shows you the whole spirit of human exploration, that people are willing to go. And I think it's really great. And I'd love to talk to you during the discussion upstairs about this, because I also try to figure out why people love aliens, why people love the idea of exploring and traveling through space to the nearest star, despite it just being so very, very far away. So my talks, I always used to say, can we go there? Not for now. And I would just close all discussion. And now all these people who love the idea so much, and others of my colleagues are really thinking of a way to send something there, even if it would take forever. It's really a real topic out there. If we can't go there, why look? Okay, and that was my first lecture, why look? So we can do remote sensing and characterize them. I'm not going to go over that today because that's a whole other lecture. We want to do remote sensing. We can learn a lot of things remotely. This is those hundreds of years since Galileo first turned his telescope to the sky. So we want to learn things remotely. But I will give a couple of slides to advertise my next lecture. That's biosignature gases. And I said before, we don't know if we're going to see aliens or if it will be bacteria. But we want to find signs of life in the form of biosignature gases that are produced by life that accumulate in the atmosphere. And that's what we talked about tomorrow. And we actually take a heart from life on Earth, life in extreme environments. They all live in very extreme environments, salty, acidic, deep inside the Earth, kilometers down in rocks, in high temperatures, down on the ocean floor. And tomorrow I'll tell you what we take away from life in extreme environments on Earth. It's not that, it is very extreme, but it's not that extreme compared to outer space and other environments. We do borrow heavily from microbes and their environments on Earth when we think about exoplanets. So if we can't go there, why look? It's because we want to do remote sensing to learn about interiors, atmospheres, and biosignatures. And to summarize this talk, I want to just give you the main points to walk away with. What can aliens see if they're out there looking at Earth from afar, or what would our Earth look like far away? It's the pale blue dot that varies in brightness with time. We could infer the presence of oceans and continents and learn about the gases in the atmosphere. When we find another Earth, I said, in the best case scenario, 15 to 25 years to find an Earth-like planet where we can do direct imaging of the atmosphere. But I said, find Earth part 2. We're generous with our definition of Earth. The big Earth around a small star within 1 to 3 years. When the James Webb Space Telescope launches, people will try to look at the atmosphere, especially if it's hydrogen rich in transmission spectrum. Can we go there? We said not for now. If we can't go there, why look? So that we can do remote sensing of properties of the planet, especially biosignature gases. Thank you.